Okay, welcome to lecture 38. So we're continuing on with numerical methods for differential equations, or let's say numerical methods for initial value problems. Yesterday we learned, or in the last class we learned Euler's method. So we're going to look at the error analysis for Euler's method here. So something that we need to keep in mind when we're solving a differential equation using numerical methods is, how much error can I expect in my solution? Okay, and we're going to do that by looking at something called the truncation error, so local versus global truncation error. And then finally, we're going to try and improve on our Euler's method. We're going to try and get a more accurate method. Okay, so that's going to be called the improved Euler method. Okay, so just a reminder from yesterday's class, we had a messy slide, but we had something called Euler's method, which said that y at n plus 1, remember we divided up our domain into discrete points, so y evaluated at x n plus 1 is equal to y evaluated at n, so at x equals n, plus h times the function, the right-hand side of the differential equation, evaluated at x n y n. Okay, and so we went through an example yesterday, dy by dx equals y, with the initial condition when x equals 0, y equals 1. And we solved that using Euler's method yesterday. Okay, and we defined these things absolute error and relative error, and we saw that these things were increasing over time, so the error was increasing over time. But we also saw that if we halved the step size h, that we roughly halved the percentage error or relative error. Okay, so here is basically Euler's method written out again. So the xn's are, so the points x are discretized, so starting at the initial condition x0 and moving in steps of step size h, so x0, x1, x2, x3, and then we have the update of y. So if we know the initial condition y0, then we can find yn plus 1. So let's say if we know the initial condition y0, we can find y1 by applying this formula, and then y2, and so on. So the sequence of values, y1, y2, y3, and so on, generated using the Euler's method will never agree with the actual solution unless the solution curve happens to be linear. But it's kind of a boring ODE, so most ODEs that you're going to solve, you are not going to get an exact solution using the Euler's method. Okay, even the first step here, remember we went from the initial condition x0, y0, even after one step we had a 0.47% error. Okay, so even after one step we've got an error. The error which occurs at each individual step is called the local truncation error. Okay, so after each individual step of Euler's method incurs something called a local truncation error. Even if if you have the solution at point xn, you get a local truncation error at point xn plus 1. So if we assume that yn is accurate, yn plus 1 will contain local truncation error, and we can use a Taylor series to derive the formula for the local truncation error. Okay, so a Taylor series of a point yn, a Taylor series around a Taylor series of the function y expanded around the point x equals a is equal to, from calculus, ya plus the derivative of y evaluated at a times x minus a over 1 factorial plus, and then these higher order terms here, so these higher order derivatives, y to the kth derivative of y. This point c here, c is some point between a and x, okay? So what we're going to do is we're going to set k equal to 1 here, and we're going to set a, this point a, that we're expanding our solution around, to be xn, so I guess the start of a step of Euler's equation. The point x we're going to say is xn plus 1, which is just xn plus the step size h here, so k equals 1, a equals xn, x is equal to xn plus 1, and if I put that into my Taylor series, I get y at xn plus 1 equals y at xn plus y prime evaluated at xn times h plus the second derivative evaluated at some point c times h squared over 2. Okay, well, I can rewrite this line as like so. Okay, so all I've done here is changed this bit that is in this curly brace here. Instead of writing y prime at xn, okay, well, I know from my ODE that y prime is equal to f evaluated at xy. So y prime evaluated at xn is just going to be f, the function f, the right-hand side of the ODE, evaluated at xn, yn. Okay, and if I ignore the second derivative term for a minute, this is exactly the formula for Euler's equation, right? Okay. This part in purple here is exactly the equation for Euler's method. So the bit that's left over, this y double prime evaluated at point C, so point C is somewhere between xn and xn plus 1, multiplied by h squared over 2, this is actually just the error. So this is my local truncation error. The local truncation error in yn plus 1 after one step of Euler's method is this leftover bit, y double prime evaluated at C times the step size h squared over 2. C here is some value of x between xn and xn plus 1. So generally it's unknown, so the exact error can't be calculated, but we can find an upper bound of the absolute value of the error. Okay, so if we define m to be the maximum value of the second derivative of y in this interval xn to xn plus 1, then the upper value of the error is going to be this m times h squared over 2. So this is what we call the local truncation error for Euler's method, and we say it's order O for order h squared, and that's because the local truncation error has an h squared in it. So the step size, the error is proportional to the step size squared. Okay, so if we double the step size, if we make h twice as large, then the error, the local truncation error, the error in each step, in other words, is going to grow as 2 squared, or 4 times. Okay, so this is a very important piece of information. It is in your table of useful information, and you will need to know it for test 3. Let's look at our example. Okay, so this is the example we were working on. We're asked now to find a bound for the local truncation error in Euler's method. So the exact analytical solution to this ODE is e to the x, or in fact to this initial value problem is e to the x. The second derivative of this exact solution, so y equals e to the x, y double prime equals e to the x as well, right? Because if I take the derivative of e to the x twice, I still get e to the x. So my local truncation error is y double prime evaluated at some point C times h squared over 2, or I could write that as e to the power of C times h squared over 2, where C is some number between xn and xn plus 1. Okay, but if we want to find the maximum possible local truncation error, the exponential function is monotonically increasing. Okay, so if C is larger, then this exponential is larger. So the maximum on this domain xn to xn plus 1 is going to be when C is equal to xn plus 1. Okay, so h, if you recall, was initially 0.1, so we can get an upper bound for the error for y1 by replacing C by 0.1, so xn was 0, xn plus 1 was 0.1, so e to the power of 0.1 is that maximum, or what we were calling m2 over here, or m or m2. Okay, so therefore the local truncation error in the first step of Euler's equation using a step size of 0.1 is e to the 0.1 times 0.1 squared over 2, which is equal to 0.005526. Okay, well, the actual absolute error that we found was 0.0052, and of course this is less than the theoretical maximum local truncation error. Okay, so well, if this is the upper bound, then it's good that the absolute error is close, but less than that upper bound. So the point is in this class, not only do you need to be able to apply Euler's method to solve an initial value problem, but you also need to be able to approximate the local truncation error in any step of this problem. Okay, we can repeat that same process with h equals 0.05. So now on the domain 0 to 0. So in the first step of Euler's method, on the domain 0, x equals 0 to x equals 0.005, the maximum value of the second derivative, e to the x, is just going to be e to the 0.05 multiplied by h squared, 0.05 squared, over 2 is 0.001314. Okay, and when we actually did this in the last class, we found something very similar but slightly smaller than the theoretical maximum. So I guess summarizing, if we try to solve the same ODE with Euler's method but using two different step sizes, we get two very different local truncation error values. So halving the step size has reduced the truncation error by 4.2, approximately 4.2. So if we take 0.005526 divided by 0.00131409, you get roughly 4.2. So halving the step size has reduced the error 4 times, which is what we expect for an order h squared method. Okay, so the local truncation error that we've just dealt with is the error associated with applying one step of Euler's method. Okay, so we assume that the value of yn was exact in the calculation of yn plus 1, but in fact it's not exact because it contains local truncation errors from previous steps. So for example, if I take the one step of Euler's method, I generate a local truncation error. If I take a second step, I generate a local truncation error, which is compounded by the local truncation error from the first step. Similarly, if I take a third step, I get a local truncation error from that step, and then that's compounded by the previous two steps, which also individually have local truncation error. So we get this build-up of error from successively inaccurate approximations. So the total error in yn plus 1 is actually the accumulation of the errors in each of the previous steps, okay? So the more steps you take, the more local truncation error you'll have to account for. Okay, so we call this total error, we call that the global truncation error. Okay, and so the global truncation error for Euler's method is of order h. Okay, so in other words, the global error grows linearly. Okay, so for example, when I solved this ODE previously with h equals 0.1 and h equals 0.05, so I have the step size here, so I should expect that the error also halves as well, right? Which it approximately does. So 2.39 is roughly half of 4.58. So this first step, table here with h equals 0.1, each individual step has larger local truncation error, but it only has 10 steps. Okay, so there's only truncation error from 10 previous steps. If I halve the step size, this solution here has less local truncation error in every individual step, but I take double the amount of steps, so I have a sort of a double the amount of compounding error. Okay. So the absolute error approximately halves, basically, is what I'm trying to say. If you halve the step size, you approximately halve the local truncation error, or the global truncation error. So halving the step size roughly halves the error, hence Euler's method has a global truncation error of order h squared. So key points are on this slide. Here is the algorithm for Euler's method. You need to know this algorithm and how to apply it. Here is the local truncation error, or the error after each step of Euler's method. It is of order h squared. So if we halve the step size, we get a 4 times reduction of local truncation error. But the global truncation error is of order h. Okay, so if we halve the step size, we take double the amount of steps. So if we halve the step size, the error at the end of the day is halved. Okay. So this slide, I suppose, is the grand summary of Euler's method. You probably need to do a bunch of examples really to become comfortable with it, and of course there is some in the assignment, and you can expect something in the test 3 as well. But in fact, we can do better than Euler's method. Okay. So Euler's method was derived from taking a linear approximation to this integral above. Okay. So we took a linear approximation to this integral, the integral of the function f between xn to xn plus 1, and we got this linear approximation here. But we can do better than that, right? So this is what we did previously with Euler's method, but we can improve our approximation of this integral. So what if instead of using the point f of xn, so instead of using this point here to approximate the area of the curve, so this integral basically, the area under the curve f curve, what if I used f of xn plus 1, yn plus 1? So instead of using this point here on the left hand side, what if I use this point here to approximate the area under the curve, sorry. We could say, what if I use this point to approximate the area under the curve, or approximate this integral, however you want to think of it. Well, if I did that, then actually the area under the curve is too much, right? So it's now over-approximated. So our Euler's method under-approximated the area. Taking this point as our approximation actually over-approximates. Okay, so Euler's method under-approximates, taking this point over here to define our area, over-approximates. If we average the two of them, though, then we get something that is much more accurate. You get a little bit of over-approximation for this particular problem, but it's much less than in using Euler's method. So we get a significantly smaller area by taking the average area of these two boxes here. Okay, and if you recall from first year calculus, this method is known as the trapezium rule. So this is actually something that you already know. So if we want to make Euler's method better, and by better I mean more accurate, we can use the trapezium rule to approximate this integral up here. Okay. So what we can say is that this integral from xn to xn plus 1 of the function f is approximately equal to the step size h over 2 times the function evaluated at xn yn plus the function evaluated at xn plus 1 yn plus 1. Okay. So we can write this as a numerical scheme. Xn is still the same, x0 plus n times h, where n is some integer starting at 0, so 0, 1, 2, 3, 4. Yn plus 1 now is yn plus h over 2 times f xn yn plus f xn plus 1 yn plus 1. So if we deleted this 2 and we deleted the second f here, that would be exactly Euler's method. But now we're getting something more accurate than Euler's method. And we're calling this scheme the trapezium scheme, or the implicit Euler's method. Okay, so this implicit scheme is of order 2, and the accuracy is order h squared. Problem is, unlike Euler's scheme, this method gives only an implicit formula for y of n plus 1. What do I mean by that? Well, I'm trying to find y of n plus 1, right? I'm trying to solve for this y of n plus 1. But y of n plus 1 doesn't just appear on the left-hand side now, like it did with Euler's method. It also appears on the right-hand side because we have to evaluate this function f at y of n plus 1 as well. So we kind of get this circular argument thing where we're trying to find y of n plus 1, but to find y of n plus 1, we have to know y of n plus 1. Okay, and just to make that maybe a little bit more real, if we have y prime, the example, this initial value problem, y prime is equal to e to the minus y plus 1 with some initial condition, the formula is telling us, this trapezium scheme formula is telling us y of n plus 1 equals y of n plus step size h over 2 times the function, which is the right-hand side of the ODE, evaluated at yn, so e to the negative yn plus 1, plus the function, the right-hand side of the ODE, evaluated at yn plus 1. So e to the minus yn plus 1 plus 1. I can rearrange, let's just say, for the first step here. So y1 is equal to y0, which is equal to 1, plus h over 2, e to the minus 1 plus 1, plus e to the minus y1 plus 1, which I can, of course, rearrange like so. But I get some nonlinear algebraic equation to solve for y of 1. Okay, so I have to solve this equation for y1 if I want to find the value of y1. Okay, this is actually possible if I wanted to use some iterative algorithm. So I can just guess the value of y1 and see if this equation is true or not. But that becomes very tedious and time-consuming. So the trapezium method is implicit, which makes finding the updated value of y challenging. So really what we want is an improvement of this trapezium scheme, which is explicit, really. We want an explicit method. So we're going to modify this trapezium scheme in order to obtain an explicit method of order 2. So the way we're going to do that is we're going to calculate an estimate of the value of y of n plus 1, and I'm going to call that estimate yn plus 1 star. And what I'm going to do is I'm going to use that estimate of y of n plus 1 in this the right-hand side of this function here, f of xn plus 1, yn plus 1. Okay, my estimate that I'm going to use for y of n plus 1 is the Euler method that I already know. Okay, so what I'm going to do is I'm going to say, I'm going to approximate y of n plus 1 using the Euler's method. I'm going to call this Euler's method approximation yn plus 1 star, and then I'm going to apply the implicit method, basically the trapezium scheme, but instead of writing f of xn plus 1, I'm going to xn plus 1, yn plus 1, I'm going to look at f xn plus 1, yn plus 1 star. Okay, so I'm going to write yn plus 1 star is equal to Euler's method, so calculated using Euler's method. Yn plus 1 is equal to yn plus h over 2 f xn yn plus f xn plus 1 y star n plus 1. Okay, so this is called this method on the right here is called the improved Euler's method, and it is an example of a predictor-corrector algorithm, or predictor-corrector method. Why is it called that? Well, I approximate or I predict the value of yn plus 1 star using Euler's method. So this is a prediction of yn plus 1. And then the second step here is correcting it or improving it. So maybe it should be called a predictor improver method, I don't know. The point is, it's a two-step method that is going to give us a more accurate solution. The value of yn plus 1 star predicts the value of y of xn plus 1, and yn plus 1 corrects the estimate up to a certain point. So the local truncation error for this improved Euler's method is order h cubed, right? So if I halve my step size h, I get that half to the power of 3. So I get an 8 times improvement in the error, which is pretty good compared to Euler's method, yeah. The global truncation error is order h squared. So if you recall, Euler's method was order h. So in Euler's method, if I halved the step size, my global truncation error was also halved. With this improved Euler's method, if I halve my step size, my global truncation error will reduce 4 times. Okay, so maybe just as a quick summary here, for all the methods, we always have this discretization of the x domain, the implicit, the x domain. For the thing that differs is how we update the y's, or the dependent variable. So we have this Euler's method, this trapezium method, and the improved Euler's method. Euler's method here is, of course, we've been dealing with that for a while now. We're happy with it. The trapezium method is the implicit method. So this is where we have the right-hand side depends on y of n plus 1. So we have some y of n plus 1 on the left and the right side, which makes things slightly complicated. The improved Euler's method is our predictor-corrector method, where we approximate the value of yn plus 1, which we call yn plus 1 star, using Euler's method, and then we update that approximation or that prediction using the trapezium method with y of n plus 1 replaced by y of n plus 1 star. Okay, and just writing the local truncation error of Euler's method was order h squared, global truncation error was order h, the local truncation error of the improved Euler's method was order h cubed, and the global truncation error is of order h squared. So in the next class, we'll start looking at some examples of the improved Euler's method, and probably solve some of these numerically as well. Because really, if you're taking 10 or 100 or 1,000 steps of this numerical method to approximate an initial value problem, or the solution of an initial value problem, well, I don't want to do that by hand, right? So really, computers are essential for solving ODEs numerically. Okay, I'll see you in the next class.